Nowadays, speech recognition systems perform very well in quiet rooms. However, their performance is still worse than desired in everyday environments, where one of the biggest challenges is cocktail party problem. We have been trying to solve this problem in the last several years. Today, I will introduce our efforts and summarize them as three trends. From mask-based techniques to filter-based techniques. From blind source separation to targeted speaker extraction. And from single modality to multi-modality. I want to apologize that since we have access to more Chinese data than English data, and since Chinese applications are our major deployment scenario, my demos are mainly in Chinese. People here all know that the task of speech separation and enhancement is to extract and reconstruct the target clean speech from audio mixture of noises, channel distortions, and reverberation. Ideally, we want to reconstruct the dry clean speech. However, many studies focus on restoring the reverb clean speech as an intermediate step. Majority of the separation and enhancement techniques operate on the frequency domain. Recently, techniques have been proposed to operate directly on the waveform. The ideal technique to this problem should be real-time and high-performing. But most importantly, it should perform well for both human-to-human communication scenarios and back-end applications, such as speech recognition systems. Ideally, we want a technique that performs well across different backends without updating them. Many techniques have been proposed over the years, and the most popular solutions can be summarized as estimating mask and applying it to the mixture. I want to point out that the mask here is a scalar value, and there is one mask for each time frequency being. Researchers have found out that estimating and applying masks generalize better than estimating spectrum directly. These masks can be estimated either with deep learning models or conventional signal processing techniques. Also note that when estimating these masks, we usually exploit spatial, frequency, and history information to improve the estimation accuracy, even though the mask itself is per time frequency being. That is, does not across frames or frequencies. For example, Professor Delian Wang and his team proposed to define an ideal ratio mask on the power spectrum and learn a deep learning model to estimate the mask by minimizing the mean square error between the true IRM and the estimated IRM. This early attempt has three limitations. First, it's not well defined at the silence segments. Second, when training the model that estimates the mask, it is not optimizing for the final evaluation criterion. Third, When reconstructing the reverb clean speech, it requires independence assumption, which is poor, especially when signal-to-noise ratio is low. The solution to the above limitations is to treat the masks as hidden variables. For example, as an output of a sigmoid function, which is limited to be within 0 and 1, and optimize for the SI-SNR on the waveforms, or mean square error on the spectrogram directly. Further improvement is to define the mask on spectrum magnitude and estimate it with a ReLU function, which has a range of 0 and infinity. Unfortunately, even this approach has two limitations. First, only magnitude of the clean speech is estimated. The phase information is not. Second, since ReLU has a minimum value of 0, the estimated masks tend to have values close to 0. This causes spectral black holes, as I will show shortly. We believe that the correct solution is to estimate complex valued masks and treat them as hidden variables. Using complex masks was first proposed by Professor Deliang Wang and his student Donald Williamson. However, in their case, the objective function used to train the model is defined on the masks itself. For that reason, they need to limit the range of the masks to, for example, within minus and plus 10. Here, we do not need to do this. And the complex masks can have any value because the masks here are treated as hidden variables. Estimating complex valued masks essentially allows us to estimate both the magnitude and the phase of the clean speech. And since the mask can take any value, we can avoid the spectral black holes frequently observed in sigmoid and ReLU masks, as shown in the spectral segment indicated by the dotted white box. Let's listen to the example. This is the ReLU mask output. And this is a complex mask output. The complex mask result is richer. The mask-based techniques can be extended from single channel to multi-channel. Let's revisit the famous NVDR filter, which is a spatial filter. Please pay attention to the basic form highlighted. Note that here both WTF and YTF are m-dimensional vectors, where m is a number of microphones. You can consider that the mask-based approach is a special case of this filter-based form. You may train a model which estimates W directly by optimizing, for example, SI-SNR, similar to that in the single channel condition we just discussed. However, till now, we found that if your goal is to improve speech recognition performance, it's better to estimate complex valued masks and then use this mask to estimate W. This observation has also been made by attendees of previous CHiME challenge. The reason is that the MVDR solution makes sure that the final filter is linear and the audio from the target direction is distortionless. Since now we have a filter instead of mask, we can further extend it to across both channels and frames. We call such a model multi-tap MVDR. We conjecture that this will help, since past frames can help estimate the current frame given structures in speech. Note that the only difference between multi-tap MVDR and the conventional MVDR is the exploitation of past frames. The rest of the problem formulation and the solution is the same. Also note that this formulation can be applied to single channel or multimodal scenarios. We did a literature search and noticed that Jacob Banesti et al. Proposed a similar idea in their 2011 book. The main difference here is that we used deep learning models to estimate complex valued masks and can achieve better final result. We conducted a series of experiments on these ideas. Here is one set of results on a 500 utterance test set. We report average results as well as results on different angles and a number of overlapping speakers. We can make several observations. First, on single channel condition, complex mask outperforms ReLU mask, which outperforms sigmoid mask. Same observation can be made on multi-channel condition. Second, multi-tap MVDR indeed outperforms single-tap MVDR across all dimensions. In fact, multi-tap MVDR achieves both best word error rate and best PASQ score. Third, PASQ score is a good indicator of word error rate only when the models are similar. It may not be a good indicator when comparing different models. For example, single channel and MVDR models here. We believe that the relatively worse word error rate in single channel models, mainly due to the nonlinear or natural distortions introduced by the model. The same observation and conclusion can be made on a different but larger and more challenging test set. Let's listen to an example. This is a two-speaker mixture plus noise.
我发现礼物盒子下面的实现我国大工程梦的一个故事。写着
This is the target reverb clean speech.
我发现礼物盒的下面的英文说明中有一行小字，写着
This is the output from the single channel complex mask enhance.
我发现礼物盒子下面的英文说明中有一行小字，写着
This is output of the conventional MVDR with complex mask.
我发现礼物盒的下面的英文说明中有一行小字，写着
And this is the result of the multi-tap MVDR.
我发现礼物盒的下面的英文说明中有一行小字，写着
The multi-tap MVDR achieves the best result. Basically, it has a better trade-off between quality and distortions. This filter idea can be further extended to across channels, frames, and frequency bands, and to conduct separation, enhancement, and deliberation simultaneously. I won't discuss them here, but will disclose the results in upcoming papers. Now let's move to the second part. In the past, we have mainly focused on the blind source separation problem, which aims to separate overlapping speech. Blind source separation is useful. For example, it allows systems to listen to multiple speakers simultaneously and can be important in scenarios such as virtual receptionist. To effectively separate the overlapping speech, the system needs to learn from training set to look for hidden regularities. The most successful techniques so far is to convert the problem to a supervised learning task with synthesized mixture data, for which the target is known. However, since A plus B equals to B plus A, blind source separation has a label ambiguity problem, which can be attacked by either deep clustering or permutation invariant training. Recently, we have spent efforts to attack a slightly different task, the target speaker extraction problem. This is because in many applications, there is information to identify the speaker of interest. The key to the target speaker extraction problem is to find the information that can identify the target speaker. For example, in the keyword spotting problem, keyword is the information to identify the target speaker. Thus, we can train a model that output the keyword feature if it's in the mixture, or output 0 if it's not. This idea can be extended to the multi-channel condition. Since DOA is not very accurate and reliable, and also because the keyword can be from any direction, we proposed a DOA-independent multi-look solution. The basic idea is to use beamformer to look at n fixed, equally spaced directions. Together with one raw microphone input, the system can use self-attention to fuse the information from different directions to enhance the keywords. The enhancement and the keyword spotting can be jointly trained so that the keyword is available, it will get more attention in the output. We notice that if we can conduct single channel enhancement at each look direction, we may further improve the performance. However, since we don't know the direction of the keyword, we adopted to enhance the speech closest to each look direction, which may or may not be the keyword. We call this improved approach multi-look neural enhancement. Here is an illustration. There are 6 microphones in the system. The system looks at 4 directions, indicated by red lines. There is a target and an interference speaker as indicated by the blue lines. Since each looker enhances the speech that is closest to the look direction, the keyword is enhanced in 0 and 90-degree directions only. In the other 2 look directions, the interfering speech is enhanced and the keyword is suppressed. However, since the attention mechanism jointly optimized with the keyword spotting will focus on the keyword, the final keyword spotting performance can be enhanced. Here is an example where there are 2 interfering speakers and 1 target speaker. This is the input mixture.
财政部部长谢旭仁答记者问。
This is the keyword.
你好，威廉。
It's obvious that it's very difficult to identify it inside the mixture you just heard. Now let's add the 4 directions. At 0 degree direction, here is the beamformer output.
财政部部长谢旭仁答记者问。
Basically, it's just a mixture of 3 speakers. And here is the neural enhancement result.
你好，威廉。
It focuses on enhancing the keyword because it's closer to this direction. However, at 90 degree, things are different. This is a beamformer output.
财政部部长谢旭仁答记者问。
It's still the mixture. Here is the enhancement results.
财政部部长谢旭仁答记者问。
You can hear that it's different from the keyword. Actually, this is an interfering speaker. Similarly, at 270 degree, we enhance the keyword.
你好，威廉。
But in the 180 degree, it enhances the interfering speech.
财政部部长谢旭仁答记者问。
However, by combining the enhanced speech with the attention mechanism, the system will be able to find the keyword from the enhanced outputs. Here are the wake up rates at the operation point where there is 1 false alarm allowed for 12 hours of continuous TV and conversational speech noise. We can observe that with neural enhancement, the wake up rate is close to 95% across all signal to interference ratio. With beamforming based multi-look system, the wake up rate is only 40% when SIR is below 6 dB. We can also observe that the inclusion of the raw input signal helps to boost detection accuracy by about 5% across all signal to interference ratio conditions. Under some other conditions, however, the speaker can be identified by the voice characteristics. This information can be extracted, for example, from the wake-up words or enrolled voice on the personal devices. Our first model for this purpose is the deep extractor network. Deep extractor network is an extension to the deep attractor network, which was originally designed for blind source separation. Deep extractor network extracts the speaker whose representation in a canonical space is closer to that of the anchor, such as keyword. Experiments show that the deep extractor network outperforms deep attractor network due to paired anchor and target speaker joint training in our model. Here is some examples. This is input.
参加表演的
播放中文民谣电台，
所以
This is output.
播放中文民谣电台。
Another example. This is input.
你如果在
中超联赛中中国队的表现怎么样？
And this is output.
中超联赛中中国队的表现怎么样？
Voice filter takes a completely different approach. It uses a pre-trained speaker embedding as auxiliary input to the enhancement network. Auxiliary information, including speaker and noise embedding, has been effectively used in speech recognition to achieve better accuracy on target speaker or noisy environment. The same idea was shown to also work well for extracting the target speech. The original voice filter can be slightly improved by jointly optimizing the enhancement network and the speaker embedding under the multitask learning framework. Our experiments show that the improved voice filter significantly outperforms the original voice filter, especially when there are interfering speakers. This suggests that the jointly trained speaker embedding provides better bias to restore the target speech. Let's listen to an example. This is the input mixture.
分类监管被确定为 A 一类公司。
It
今年
contains
7月
three
29
people.
日至8月6日，
It contains 3 people of speech. This is output from the enhanced voice filter.
打开飞利电视。
Now let's move to the last part of my talk. I just mentioned that you can use speaker embedding to extract the target speaker's speech. However, when we remove the single modal restriction and assume access to multimodal information, we see greater potential. In the figure, we can see that in such a system, there are at least 4 possible inputs: the multi-channel mixture speech, the directional feature extracted from video and audio, the lip movement from video, and the speaker embedding from audio. Here is a simple comparison between different approaches. The voice filter we just discussed uses only audio information to identify the speaker. The look into listen technique only uses the face embedding to identify the speaker. The multimodal solution we have been working on exploits multiple sources of information. I have demoed the voice filter result. Let's listen to an example from the look to listen technique. This is the input.
Toward market reform, and in the end we entered the WTO. So therefore, over the last 20 years, China's economy has maintained a double-digit speed.
Basically, there's a translator to translate text. The output only extract one language.
加速改革，包括最后进入 WTO 啊，所以使过去20年中国这种经济保持一种双位数的高速成长。
We can clearly hear the artifacts in the reconstructed speech. Here is a multimodal target speaker extraction example. When the speaker is facing the camera, which is considered as an easier case. This is a mixed speech.
列出3个方程，才能够求解出我们刚才的这3个未知数。
This is an extracted speech for the lady with a green box.
今天很高兴能够在这样美好的下午跟大家一起。
Here is another example where the target speaker is only showing the lateral face. This is a harder case. Again, this is a mixture.
所以一个个关于战争、关于爱情、关于所有的一切的东西。
And this is extracted speech for the gentleman with a red box.
所以一个个关于战争、关于爱情、关于所有的一切的东西。
However, not all information sources are equally important. To figure out the importance of each information source, we conducted ablation study. This table indicates that if only one source of information is available, directional feature is most important, followed by the speaker embedding. The least important is the target lip information. However, when two sources of information are available, the importance of the rest is significantly lower. More interestingly, when lip embedding and the directional feature are available, with or without speaker embedding causes very small difference. In many applications, speaker embedding is not available, but luckily, this seems to be fine. Comparing to single modal systems, multi-modal systems are more robust. In this example, if only directional feature is available, the target speech will be over-suppressed when the speaker slightly turns his face, as indicated by the yellow box. If only lip feature is available, there will be leakage from interfering speaker when the speaker opens his mouth without speaking, as indicated by the green box. There is no obvious issue when both information are available. Here we systematically evaluated the system robustness when one modality is missing or inaccurate. The left table indicates that if directional feature is accurate, the SDR is only slightly worse, even when 50% of the time the lip information is not available. That is, the system is robust to lip dropping. However, the lip information is still important when speakers are close to each other or the target speaker is not facing the camera. The right figure indicates that errors in directional feature, which in many cases is less than 5 to 10 degrees, only severely affect the performance when the angle between the target and the interfering speaker is less than 15 degrees. Another important question in multimodal system is information fusion. This is the whole architecture of our multimodal speech separation and enhancement system. The fusion model takes an important role. We studied several possibilities. We found out that simple concatenation works pretty well. However, by using factorized attention fusion, which is similar to multi-head attention, we can achieve even better enhancement. Multi-modality can also help improve diarization. This is because with multimodal information, the decision can be made with more information. There are several limitations in the state-of-the-art audio-only diarization system, such as UIS, RNN. These limitations can be alleviated in the multimodal system. First, in UIS RNN, the hypothesis would include unbounded number of possible speakers. In the multimodal system, the number of speakers can be determined by the face detector. Second, the audio-only system is difficult to identify two speakers with similar voice, while this can be easily solved with facial information in the multimodal system. Third, UIS RNN requires labeled data to train well, while multimodal system can exploit the correlation between modalities to conduct self-learning. Fourth, in the multimodal system, the system can link the voice to the face to identify the speaker, which is not available in the audio-only solution. However, there are challenges that are specific to the multimodal diarization systems. One of the key challenges is the synchronization between the audio and the video signals. Due to the hardware and the speed difference between light and sound wave transmission, there will be random synchronization errors in the raw input. To solve this problem, we designed a sync layer which computes the correlation between the audio and the video signals and align them accordingly. This sync layer is jointly optimized with rest of the model. Our experiments indicate that our multimodal diarization system can cut the detection error by 1/3 over UIS RNN, the state-of-the-art single-channel diarization system. In addition, the multimodal system can attach the face of the speaker to each segment, which is not doable in the audio-only solution. Let's see a demo on a real recording. As you can see, this is a really challenging scenario. And the system seems to perform well. Multi-modality can also help improve speech recognition. LRS2 is a relatively clean speech corpus with multimodal information. The table here indicates that although video alone performs very poorly in transcribing speech, exploiting it in the audio plus video setting helps reducing error rates. The table also indicates that our system is not bad. It outperforms the prior arts on this task. Multimodality helps more on overlapped speech. Here, we explored different ways of fusing audio and video information in acoustic models if we adopt an integrated enhancement and recognition model. The first approach simply concatenates the audio and lip embeddings. The second approach estimates a soft gate using the lip movement information and apply it to the audio embedding. The third approach estimates the gate with both audio and visual information. We found that among these three architectures, exploiting the audio-visual jointly determined gate performs best. These gates can be considered a soft VAD or the masks we discussed before. The best approach achieved 10.3% word error rate on this task. We compared the integrated acoustic model we just discussed, in which separation and recognition are conducted with a single network, with the pipeline system, in which we first extract the target speaker's speech and then recognize it. In this latter setup, the target face is used in both steps, and the separation and recognition components are jointly trained as a multitask learning problem. Experiments show that the pipeline system outperforms the integrated system so far. We can reduce the error rate from 10.3 to 8.6%. In summary, I introduced our attempts in solving the cocktail party problem along 3 lines. We believe the mask-based speech separation and enhancement will be replaced by the filter-based approach. However, the trade-off between the model flexibility and the distortion introduced by the system need to be further studied, maybe through enhancement and ASR joint training and evaluation. While blind source separation is important, we may be more interested in target speaker extraction in some applications. In such setups, the key is to exploit the information that can identify the speaker, which may or may not be the speaker's voice characteristics. We observe that as hardware becomes cheaper and on-device computation is more powerful, multimodal information will be more easily accessible to the system. Multi-modality is much more robust and better performing than single modality. However, our study is still preliminary. Better models of separation and recognition are yet to be found under the multimodal setup. I would like to thank my colleagues and our interns who contributed to this study. Due to time limitation, I cannot cover all the details. I listed the papers discussed in this talk in case you would like to know additional information. Thank you.